Okay, so we're going to learn about some objects. Now. We're going to convert our fraction implementation into some objects and learn how those work, and then we're going to write a small game, an implementation of Tic Tac Toe that you can use as a model for your homework assignment, which is to write an implementation of the game Connect 4. Text-based. No like boards and actual checkers or anything like that. So we'll talk more about that here in a little bit. But for starters, I'm going to go ahead and get rid of everything that's inside of main for now. We'll leave our implementation down here because that's going to become handy here in a few minutes. We're just going to move that stuff around. We want to understand how we can represent our fractions in terms of objects. All right. So for the first time, we're actually going to create a separate file. So we are in 535 Spring 2016 inside the source directory. Right now we just have a file called driver.java. I'm going to go ahead and right click and we're going to create a new class called fraction. All right. So typically classes have uppercase names. So a class usually starts with an uppercase character. So we called our class here called fraction. So objects typically have a name starting with an uppercase letter. These guys are a collection of constructors, fields, and methods. Those are the types of animals that live inside of objects. So an object is a collection of constructors, fields, and methods. Fields, these are variables owned by the object. Constructors are specialty method, especially methods for initializing an object, and methods are reusable chunks of code owned by the object, just like the methods we have already been writing. All right, so nothing new on the method side of things, except the static keyword. We'll see that. But we've already created variables as well. Now they're just going to live inside of objects. And we've already actually created a constructor. We just didn't know it. So we'll learn about those things here in context. So we're going to have a class fraction. So let's talk about the fields first. So the fields are the attributes we need to remember about a fraction. So in our world, the attributes are going to be we'll keep it as long since we did that in the other one. So we'll have a long numerator and a long denominator. Those are our two fields. All right. So every fraction has a numerator and has the denominator. All right. That's our fields. Now we might add some additional fields for some other objects that we do. When we create our tic-tac-toe game here in a few minutes, we'll see that sometimes you have multiple fields, but we're keeping fractions fairly simple because that's what a fraction is. Remember, the whole purpose of object-oriented programming, this goes back to our example where we said the object-oriented telephone looks like a telephone. The procedural telephone looks like a pile of wires. So if we were to visualize what a fraction looks like, it looks like a numerator and a denominator, right? Two pieces of information we need to remember about a fraction, the numerator and the denominator. Okay, now we need a constructor. So the constructor is going to be the guy who builds for me a fraction. And if you remember from earlier, I purposely named this function that took in a numerator and a denominator and created for me a fraction. I purposely called him a constructor. I said construct fraction. Constructors are the methods always, constructors are always named the same as the class and set up the initial state of an object. So having said that, our fraction always has the same name, or constructor for our fraction always has the same name as the class. Class name is fraction with a capital S. Constructor's name is fraction with a capital F. I think I said S, but I meant F. Not sure what I said. And this guy is going to take in a long N and a long D. And we'll set numerator equal to N and denominator equal to D. Like that. That's our constructor for a fraction. Now, realistically, this is fairly poorly written code right now. And the reason for that is we don't necessarily know what N and D are. We probably want our parameters to be more descriptive than that. So we probably want these parameters to be numerator and denominator. The problem is, if we do that, confusion begins. Remember our statement that all variables resolve to their most local definition. Right here, what am I trying to do? My intent is to set this numerator equal to this numerator. So my intent is to set the field associated with this particular fraction equal to the numerator field associated with this particular fraction equal to the numerator that was passed in. But as it's written, this variable will resolve to its most local definition, which is this one. This variable will resolve to its most local definition, which is also this one. So I'm in no way changing the values of these guys up here. I have to have a way of talking about this particular fraction's numerator and denominator. And we do that using a special keyword called this. Okay? Like we talked about last time, the new keyword gives us, that's our real estate agent, it gives us a memory address. The this keyword is how an object refers to itself from within itself. That's the this keyword. So in real life, this for us would be like me saying, well, I just said it, me, my or I, my name is Mike. So inside of my head, when I refer to myself, I say my name. All right? So my is the same thing as this. It's how an object refers to themselves from within themselves. Okay? We refer to ourselves in the first person. Okay? I, me, my, that type of thing. So if we are inside of our implementation of fraction, when I want to talk about my numerator and my denominator, if I am one of these fractions, I do that using the this keyword. So I'll say this dot numerator and this dot denominator. In this case, I'm saying set my numerator equal to the numerator that was passed in. Set my denominator equal to the denominator that was passed in. That make sense? So that's how we refer to our internal fields. There's also the other advantage of this. If I type in this dot, it'll spell it for me, just like the driver dot thing from before. So this dot shows me all of the things that are owned by this fraction. All the things that I know about if I put myself in the shoes of a fraction. Okay? So the constructor initializes our fraction. So when we build a fraction, we'll be passing in a numerator and a denominator. The constructor will set his numerator equal to whatever was passed in and his denominator equal to whatever is passed in. Okay? So let's just leave it at this for right now. We haven't put a whole lot of functionality into this yet. But if you think back to when we talked about structs, when we were talking about the evolution of our programming languages and we made that jump from C++ or from C to C++, we talked about how C had structs but didn't have this thing called a class. And a class is kind of like a struct that also has functions in it. And then we went to Java, and Java got rid of structs, saying that, oh, well, basically a struct is a class that doesn't have methods. Well, that's kind of what we're looking at here. Constructors are, let's just say they're not methods right now. They look like them, but they're not actually. Because notice that a constructor does not have a return type, and we'll talk about why here in a few minutes. So as we have this thing set up right now, we effectively have a struct called a fraction. All he does is manage two variables, a numerator and a denominator. Let's see how we can use this guy. So we're going to come back to our main here. We're going to say fraction f1 is equal to a new fraction. Fraction f2 is equal to a new fraction. There's our 1/2 and 1/4. And then we'll say system.out.println f1. What do you think the output of this program is going to be?
Right now, you can see on the screen is you're just going to see whatever's in f1.
What is in f1?
1 and 2. No, you're going to see the memory address.
Ah, memory address. Why?
Because you're just giving it, because that's all the f1 is. You're just telling it a pointer right now.
But how do you know it'll be a memory address?
Well, because we saw it before.
Well, you've never seen objects before. You've seen arrays. This is something new. Pun intended.
That's all I know right now.
I just gave you the answer when I said pun intended.
Oh, new, yeah.
What does that guy do? New keywords, our real estate agent. He goes and gets us memory addresses, right? So I don't care what's on the left-hand side of this equal sign. If this dude's involved, he's giving us a memory address. That's what he's doing. All right? So this is going to print out a nice memory address that has a little fraction-y twist to it. It's the fraction at that crazy memory address. All right? It's still a memory address. Not that pointers exist any more now than they did 5 minutes ago.
Excuse me, sir. I'm sorry. I have to go to Minnesota this night, and I have like ticket on around 11.
It's fine. Just watch the video. It's fine.
Thank you.
All right. So right now this prints out the memory address, right? All right. So we have our two fractions. We want our fractions to now be able to do some stuff. Now, just to show you here, if I wanted to print out the numerator, I can say f1 dot numerator, and that'll let me get at the numerator. That'll give me the 1. I can say f1 dot denominator, and that'll get me the 2. Okay? So at this point in time, what we've really done is we've created an abstraction that works kind of like our two-dimensional arrays do, but instead of saying f1 at bucket 0, we can just say f1 dot numerator. A little bit cleaner, right? Now the reality is after we get a little bit deeper into object-oriented programming stuff, we're going to see that we are not allowed to directly access those things. So to show this, I'm going to make these guys private. We have 3 different security settings for fields, as well as methods. We have public, we have private, and we have protected. Now, we're not going to talk about protected right now because we're not going to talk about inheritance till next class. But public and private are on the table. For us, everything that's a field will be private. Good rule of thumb. We come in here, let's just talk about the security settings. We have public, private, protected. Public means anyone can access this. Private means only accessible from within this particular class. Protected means only accessible from within this class or children of this class, which we're not going to talk about yet. All right, so this is us securing members of a class. So we can put public, private, or protected in front of fields, in front of methods, and in front of constructors. Okay. We've actually seen this in front of a method before. Notice here in driver, we've seen public in front of our main method. We just always kind of ignored it. This guy has to be public because we've mentioned that all programs begin and end with main. The Java virtual machine has to have access to this method. That's why it's public. So that things outside of this class can access it. All right? Without going too deep into that, we will talk about it, but without going too far into it, we're going to just introduce a rule of thumb. So, security rule of thumb. Make everything private and then loosen the reins as necessary. All right, so we're going to lock all the doors and only unlock the few of them that we actually need to have unlocked when we need to have them unlocked. So one pattern that I'm hoping you're starting to see as we're starting to go through some of these larger solutions to problems is that in many ways we are organically growing solutions. We start off with a seed and then let our solution start growing from there. So that's why I introduced this rule of thumb. When you first create a field, for example, that's where we're going to be really focusing on these right now is in terms of our fields. When we first create a field, make it private. And if you run into a situation where having it something other than private would be handy, then you can make it something other than private. But your go-to move is to make it private. Now let me show you in practice what these words mean about making it private. So when I said private, I'm saying it's only accessible from within this particular class. Where the rubber hits the road here is if I'm in the fraction class and I make my numerator and my denominator private, I'm saying I can only directly access these fields from within the class name fraction. Make sense? Which means that if I go back over here to driver, I'm going to have an error. Because I've tried to print out the denominator from F1. The denominator, as we defined here, is a private field. And I'm trying to access it directly here inside of a class called driver. Is that the class named fraction? Nope. We can't access private fields of the fraction class inside of a class named driver. Make sense? So does that mean we loosen the reins? Well, based on what we know right now, the answer would be yes. But we have a workaround. Because here's the issue. Just for a moment, I'm going to go ahead and we're going to loosen these reins. We'll set it to public. So now, I can access the denominator. But actually have a little bit more access than I maybe intended. Can also change the denominator from outside. Okay? So realistically speaking, we think about this in real life, we might want to have the ability for somebody to come and ring our doorbell and ask us for something. But they shouldn't necessarily be able to just walk into our house at their leisure and change things, right? So we're giving them access to us on a per request basis, instead of us just giving them free-for-all reign over our house. Make sense? So if we were to say that, give permissions to this guy, we would say that our denominator right now is both read and write. The door is unlocked. You can come in and take whatever you want. All right? Now, if we lock it back down, we no longer can read the denominator, but we also can no longer write to the denominator. We're probably relatively happy about that side, but this side is a little limiting. So what we can do is we can write something called an accessor method, okay, or a getter. So let me just talk about those real quick. They're just funny names for normal methods. Historically, so access to private fields. Historically, we had accessor methods. These provide read-only access to a private field. And we have mutator methods. These provide write-only access to a private field. But what's nice about this is mutator methods allow us to include logic before letting them change the value. So the idea is let's say that we're going to have that, let them change the denominator. And let's say the denominator always has to be something greater than 0. All right? If they try to change the denominator to something 0 or less, we can ask, if you tried to change the denominator to something 0 or less, don't let them do it. We won't let you change it. Only if you provide us a value that's big enough will we let you change it. Accessor methods basically provide access to a private member, and we'll see how these work. These are old names. So these are all they are is names. These aren't all of these are just methods. They're normal methods. We're just giving kind of a descriptor to these methods. Accessor methods are more commonly known as getters today. Okay, these guys are called getters. Mutator methods are commonly known as setters today. So these are getters and setters. Okay? Getters are going to be very common. So we're very commonly going to lock down a variable completely and then expose it for read-only privileges through a getter. So let's go ahead and see this. So we'll go back into fraction, and I'm going to go ahead and we'll just call these getters. And this is going to be a method that exposes our numerator. So it's going to be a public method that returns a long called getNumerator, and this guy returns this dot numerator. And then we'll have another one, public long get denominator, and this guy returns this dot denominator. Those are getters. These guys are public, so they are accessible outside of this class, and they are providing read-only access to this private member. So we are not allowed to change this guy through this getter. We can only access the guy through the getter. So now if we want our denominator, we say f1.getDenominator. So we're using a public method to access a private member. Make sense? All right. This would be the preferred way of writing this stuff. Have everything private, and then loosen the reins as necessary or provide access as we need. Now, a nice little trick we can do with Eclipse, because these getters and setter things are pretty common. I'm going to go ahead and just delete these here for a second. I'm going to right click out here, and we're going to go down to source, then generate getters and setters. Click on that, and it's going to show me my fields. Now, if I just click the box next to these, it's going to generate both getters and setters for these. But if I hit the drop down, I could say, just give me the getters. Don't generate the setters. All right, and it'll allow me to set other things like, do I want them to be public or whatever, but generally you just leave everything else alone. Just say okay, and there's our getters and setters, our getters for those. It's what we just wrote, right? And they didn't have to be called get numerator or get denominator. We could have called it elephant circus if we wanted to. Not a great function name if its purpose is to give you the numerator, but we could have called it whatever we wanted. Okay, there's no rule that says a getter has to be called get numerator. All right, that just happens to be a naming convention. All right, so we've exposed our numerator and our denominator to the outside world through these couple of functions if we need it. Okay, but what we've done is we've also protected access to our numerator and denominator, where we are not going to allow it to be changed directly from outside of the fraction class. We can only modify numerator and denominator if we're inside this class, because these are both private. Make sense? All right, so now let's go ahead and teach a fraction how to print itself. So we'll say public void display, and we're going to go ahead and say system.out.println this dot numerator concatenated with a slash concatenated with this dot denominator. And I am inside the fraction class, so I am therefore allowed to directly access these private fields. So now if I ask a fraction to display itself, which is a public method, a fraction will be able to display itself. So now I can come out here to driver. And I can say f1 dot display. Now we'll get our 1/2. We have asked our fraction f1 to call his display method. Now notice that I do not have static in front of this guy. All right, so I'm going to introduce half of the story here. I'm going to tell you the story, but we're not going to explore it real deeply because we need to get to some other stuff. Otherwise, your homework is going to be harder than it might otherwise be. Because my intention is for it to be trivial this week. Hopefully, I'm going to give you a good, solid foundation with Tic Tac Toe that you can build on top of that for your assignment. So, methods. We have static versus non-static. Static methods are owned by the class in which the method was defined. Non-static methods are owned by an instance of the class in which the method was defined. Static methods are called using the name of the class in which it was defined. So finally, let me pause here for a second. I said static methods are called using the name of the class in which they were defined. So out here inside of driver, I still have a method called GCD, for example. It's a static method. Therefore, we call this guy using the name of the class in which that method was defined. So I say driver.gcd to call that guy. Now, up to this point in time, we've seen that we can actually just say GCD. And why is that? Because inside of a static method here, we are in what is known as a static context. And what that effectively means for us is everything is assumed to have driver dot in front of it. Make sense? When I'm in a static context, everything is assumed to have the name of the current class dot sitting in front of it. So even though we don't see it here, that's assumed to have driver dot in front of it. Now, just because you don't have to use driver dot, I would still suggest you do to minimize spelling mistakes. Because if I say driver dot, it gives me my options. There's GCD, I can press enter, and it fills it out for me. That's a handy thing that Eclipse will do for you. All right, so static methods are owned by the class itself in which it was defined. And we call it using the name of the class in which it was defined. Instance methods, let's go back here. Non-static methods, these are often called instance methods. Non-static methods are instance methods, are owned by an instance of the class in which the method was defined. They are called using an instance of the class in which it was defined. And what do I mean by that? Come back here into fraction. Inside fraction, we have a non-static method here called display. That's an instance method. It's owned by individual instances of the fraction class. And what does that actually mean in practice? That means that F1 has his own copy of the display method that knows everything about F1, including that his numerator is 1 and his denominator is 2. F2 has his own copy of that instance method, which knows everything there is to know about F2, including that his numerator is 1 and his denominator is 4. Make sense? And just to take this one step further, I'll make this public. It's not necessary, but I don't want to have to talk about what it means if I don't put anything in front of there right now. Actually, I'm going to call this guy display 2 just so it doesn't, actually let's call it display static. All right, and it's going to be void. Okay, so public static void display static. What would we intend on this guy to do? Because we are inside of a static context here, everything is assumed to have fraction dot in front of it. Static contexts do not have access to this. That is this dot. So we don't have this dot numerator. We don't have this dot denominator. Why? Because we are not owned by an instance. We are not part of fraction 1 or fraction 2. We are owned by the class itself, the fraction class. We don't know about an individual fraction's numerator and denominator. Anything that happens inside of here is a class method. Okay? Or is owned by the class, so it happens within a static context. So if I call this guy, we mentioned that static methods are called by the name of the class in which they're defined. We cannot call F1 dot display static. So F1 dot display static, notice this guy is listed as a static method. We call him using fraction dot display static, using the name of the class in which that static method was defined. Make sense? All right. So those are two different types of methods. Each one is not better or worse than the other. Okay? It depends on the job you're solving. In this case, we want individual fractions to be able to display themselves. We want individual fractions to be able to advertise their numerator to us or their denominator to us. So those are all going to be instance methods because we want them to have access to the this keyword, to the variables associated, the fields associated with that particular fraction in this case. Make sense? All right. So as opposed to class methods, which we've been writing all along, these static methods. So static methods are often called class methods. These guys typically take in all the input they're going to need to work on and do their thing because they don't have access to fields up above. That's about a half-truth because we can actually have static fields if we wanted to, but for right now, let that comment go. All right, so for our intents and purposes, class methods typically are going to take in all the parameters that they need to do their job because they don't have access to anything else. Instance methods only need to take in the additional parameters that they need to do their job over and above the things they already have access to inside the class through the this keyword. Make sense? So let's explore this a little bit by fleshing out our fraction class with the things that we've already written for fractions. All right, so adding fractions and that stuff. All right, so go back into fraction. So I'm going to get rid of the display static because it's purposeless. So we would like to be able to add some fractions. That is to say, a fraction should be able to add themselves, this, to another fraction, to a given fraction. So I should be able to have a function called something that returns public that returns a fraction called add that takes a fraction as a parameter. And what am I saying in here? This is add myself, that is this, to f, the fraction that we passed in. I don't need to take in two fractions because the guy who owns this add method knows about himself. He is a fraction. That's parameter 1. We already have access to his numerator and denominator. We only need to take in the fraction we're adding him to. Make sense? Okay. So what was our logic here? So we take in our fraction, f, and what we need to do is first find a common denominator. So we're going to say long common denom. And this guy is going to be equal to this dot denominator times f dot, do I do get denominator? Get denominator would definitely work. But wait a minute. Isn't denominator private? What does it mean for a variable to be private? You can only access that variable inside the class named fraction. Notice that was very specific how I said that when I introduced it. I didn't say that private fields are only accessible within that copy of the fraction class. They're only accessible inside of any class identical to this one. So even though this denominator is owned by a different fraction than this fraction, we are still inside of the fraction class. And therefore, we can directly access his private fields. Now, having said that, there is nothing wrong with calling get denominator. We can use that anywhere. Right? It's going to give us the same value, and since we don't have an intention of changing his denominator, it's not going to make a difference. Make sense? But it is important to understand that just because that guy's private doesn't mean he's locked down from everything. It means he's specifically accessible under a very specific circumstance. And that is if we are inside of the class where he's private, which we are. We just happen to be inside of a different instance of that class. All right, so I'll switch it back. We'll leave it as the f dot denominator here. So that's going to be our common denominator. Then we'll have our long num1 is going to be equal to this dot numerator times f dot denominator. Long num2 is equal to f dot numerator times this dot denominator. And then we're going to go ahead and we're going to return, well, here, I don't want to return it yet. Let's say fraction answer is equal to a new fraction, passing the new numerator, which will be num1 plus num2, and the new denominator, which is common denom. And then we'll return our answer. So, same logic we had before. We just now did it in terms of fraction objects. Make sense? So this will now give us our new fraction. So I can go back out to driver, and now I can say fraction f3 is equal to f1 dot add f2. Similarly, I could say fraction f4 is equal to f2 dot add f1. Those guys should give me the same answer, right? In this case, I'm asking f1 to call his add method, taking in f2 as a parameter. So f2 will come in for f, and f1 is internally referenced as this. So when I'm inside of f1's add method and I say this, right here, I'm talking about f1. That's how an object refers to itself from within itself. Because I don't have access to a variable called f1 in here. I only have access to something called this. Similarly, if I have f2 call his add method, inside of that add method, this refers to f2. Okay, and there's f1. Now, just to prove that this is the case, comment that out for a second. I'm going to go ahead and we're going to print out system.out.println f1. So I'm going to print f1 out there, and then I'm going to print out this inside of add. Okay? I just advertised. Now notice, the only printing we're doing right now should be those two pointers. I'm not doing any fraction displaying right now. I've commented that all out or deleted it. So out here, what am I doing? I'm printing out the memory address of f1. But right before I do that, I'm calling f1's add method. And in that add method, what am I doing? First thing is I'm printing out the value of this, which will be a memory address. Now, if what I'm telling you is true, if this is a synonym for f1 inside of methods that f1 is calling, it's how an object refers to itself from within itself, I should see the same memory address printed twice. Outside of this guy, this is f1. But when I'm actually calling one of f1's methods, this is his memory address. So we should see the same memory address twice. Make sense? So proof that this and the variable that called the instance method are the same thing. Okay? And I'll go and ask F3 and F4 to display themselves, and you'll see that they're the same. So both of these guys should be 6/8. Oh, we're still printing out the value of this inside of add. We'll take that out here. So didn't matter who I added to who, because of the nature of how fractions add. It's the same answer either way, right? Go back in here. Let's get rid of this guy. All right. So now let's go ahead and teach a fraction how to reduce itself. Actually, we're going to just say void reduce. So we're going to ask a fraction to reduce himself. We don't have to provide him with another fraction. He already knows about himself. He knows about his numerator. He knows about his denominator. All we're doing is we're pointing at one of our fractions that you reduce. And he's going to go and he's going to update his numerator and denominator to be the reduced versions. Make sense? All right. So, out of curiosity here. No, we don't. So I am going to steal our GCD function here. We're going to paste it into our fraction. We'll make it a instance, but I'm going to make it private. We only have access to GCD inside of our fraction class because that's something we're internally using, right? We don't need to expose that to the outside world. Now, let's connect this back to something we said weeks ago. Remember when I talked about the object-oriented telephone? I said all the details are inside, but only the public interfaces are exposed. This is an example of one of those details that's going to be important to the inner workings of our fraction, but is not actually something that we're going to publicly expose to folks outside of the fraction class. Since I made this method private, I don't have access to f1.gcd out here because it's a private method. Make sense? I've chosen not to expose it. That guy's equivalent to those wires that we know are there inside that telephone, but are hidden inside the nice case. Starting to see how some of those pieces of things I've said before are coming together? All right. So GCD takes two values and it goes through and does its thing and gives us the greatest common divisor of both of those guys. I made it private so we only access it from within our fraction class. We actually could have made it static as well. Because does every fraction need a copy of this guy? No. Let me ask you this. Does this guy need to have access to a numerator or denominator? Or is he really just a tool that all fractions use? It's a tool. So this would be actually a good example of this. So I'm going to actually make this guy static as well. So now he's a static method, which means he's owned by the fraction class, not a particular instance of the fraction class. He's also private, so we're only even allowed to use him if we're inside of the fraction class. So in reduce, the first thing we're going to do is we're going to say long divisor is equal to, we need to call our GCD function. This is a private function, so he's only accessible inside the fraction class. Good news is we are currently inside the fraction class, but he's also a class method because it has the word static out front. We call class methods using the name of the class in which the method was defined. The name of this class is fraction. So we're going to say fraction dot GCD, and we're going to pass it this dot numerator, this dot. I threw it off when I was doing this. GCD, this dot numerator, this dot denominator. I could have typed it out, I just wanted to let it do it for me. Okay, so that's going to give me my divisor, and then what am I going to do? I'm going to say this dot numerator divide equal divisor, this dot denominator divide equal divisor. Or we could say this dot numerator equals this dot numerator divided by divisor. this dot denominator equals this dot denominator divided by divisor. It means the same thing. So now we can ask a fraction to reduce themselves. Come back in here. So I'll go ahead and I'll tell F3 to reduce himself. In fact, let's actually do that before we display it. So F3 and F4 should both be 6/8, right? We'll ask F3 to go ahead and reduce himself. Notice I didn't need to pass in anything. I pointed at F3 and I said, you, reduce yourself. And he did his internal magic to reduce himself. So now from this point forward, F3 is now 3/4. Similarly, when I tell F4 to display himself, we never told him to reduce. So he's going to still be 6/8. So there's our, woo. Whatever it is, I'm sure I did it on purpose. Let's see. Oh, it's our GCD, this guy down here. We have a, when we took GCD out, we should probably not call it anymore after we remove it. I will. The GCD, the stuff that, are you talking about the fraction stuff? Yeah, I did. But I'm also, we'll have it in here too. So you'll have all the stuff. We haven't lost anything. Okay, so, yeah, inside fraction, we have all of our stuff. This guy now knows how to display himself. Here's our 3/4, here's our 6/8. Make sense? All right, so that's a pretty decent crash course on objects in terms of fractions, which we worked on for a while today. So before we move on and look at a small object-oriented text-based game, are there, actually let me do one extra thing here just to introduce a concept. Let's say that we wanted to read in 2 fractions from our user. Have it build 2 fractions, add them together, and display the reduced result. Because we haven't done user input in here, right? And we're going to need it for our homework assignment. So let's go ahead and let me show you how user input works. User input in Java actually used to suck. It was several lines of code in order to read something in from the user. It's actually much easier now. We have something called the scanner. All right, and it's going to want us to import scanner. So that's java.util.scanner. So similarly, how we imported random before, now we're importing scanner, and it'll do it for us. So we have this thing called scanner, and scanner allows us to read in from something called an input stream. Now we're going to use scanner for some other things at a later point in time, but right now we're only really interested in reading in from the keyboard. That's the magic that we need this moment. So just like we've been using system.out to write stuff out to our screen, that's called standard output, system.in is the default input method, which is our keyboard. So I'm saying I want to build a scanner object. This is no different than we build a fraction object. Notice these syntaxes are pretty similar to each other. What am I building? I'm building a variable named f1 of type fraction, and he's going to be a new fraction, and our fractions took in 2 parameters, a numerator and a denominator, right? Same thing's true for scanner. I'm going to build a variable. I named it input. He is of type scanner, and he's going to be equal to a new scanner, and this constructor for scanner must take in an input stream. Evidence would suggest it takes in an input stream, seeing as though I told you system.in is an input stream. We don't have to know what input streams are right now. We just happen to know that they are important things to get stuff from our user. And scanner lets us do it conveniently. Make sense? So what we're going to do here, let me just get rid of that stuff. So we're going to go ahead and ask our user for a couple of pieces of information. So we're going to say system.out.print. Please enter Actually, let me do it this way. We'll just throw it all up here. I want to get through it fairly quickly. Please enter a numerator. And then we're going to say long num is equal to input dot next. Let's see, is that going to be good for? Yeah, that'll work. Input dot next long. Typically, what I would do is I would say input dot next line, which gives us a string, and then I would pass that guy to what we were introduced last time to integer.parseInt, right? In this case, we're dealing with longs. I would pass it to long.parseLong. So as a matter of trivia here, notice that we have these object types. We have integer, we have long, there's one called character, there's one called Boolean. And we know that they're object types because they start with a capital letter, as I've advertised, right? Now remember when we talked about the two different kinds of variables? We talked about primitive type variables and we talked about object type variables. Okay, what was the definition of a primitive type variable? Said it's a variable built into the language that can only hold a value. That's the extent of its capabilities. So the follow-up to that would be, why do we have all these objects that are counterparts to our primitive types? Why do I have an integer class? Why do I have a long class? Integers and longs can't do anything to themselves. They don't have the extra functionality. So those guys have classes that add additional functionality to integers and longs and characters and that kind of stuff. That make sense? Follow up, here's a method called parseLong. I'm calling it by something called long. Based on what I've told you, long, well, I think I actually specifically said what it is, but based on our naming conventions, long is probably what kind of animal? What kind of thing is long here? It's an object. How do you know it's an object? Why would you suspect it's an object other than the fact I told you it is?
Well, it's capitalized.
Capitalized. That's the exact answer I'm looking for. We want to start seeing patterns because noticing patterns in these things tells us a lot as long as they're consistent. And they are. Most programming languages have consistent patterns. So we know this guy's, well, we highly suspect this guy as an object. We'll look at documentation next time and prove it, but we highly suspect he's an object. So if he's an object, what kind of animal is parseLong? It's a method, right? Because it has the parentheses, parameters. What kind of method is it? Is it a class method or an instance method? Is it a static method or a non-static method? How do you know? You think it's a non-static method? Okay, tell me why you're wrong. How do you call class methods? Are called using the name of the class in which it was defined. How do we call instance methods? Using an instance of the class in which it was defined. We're calling this method using the name of a class. Therefore, he must be a class method, a static method, or this is bad code, one of the two. And since we've already covered that I never write bad code, this guy must be a class method, right? Okay. So, case in point, this line right here, I'm just going to comment that out for a second, is equivalent to input.nextLong. Those two things do the same thing. The scanner class has built into it a convenience method for parsing a long out of a string for you, so you don't have to do it yourself. Make sense? For your homework assignment, you'll be reading in integers because we're playing Connect 4, so you'll be asking which column 0 through 7 should I be dropping my checker into? So you'll be reading in some integers. Okay, so if you want to read them in as a long, you can. Otherwise, guess what? There's an input.nextInt as well. Okay, so here, I'll show it to you. That way I don't get any feedback that you said we couldn't use that. So there's our next int right there. All right, but it just so happens that we require longs to build our fractions. So we're going to read in a long. So there's our long num. Then we're going to go ahead and ask for a denominator. And we'll read in our long denom from our input. Then we're going to do this exact same stuff again to get our other two things. But first we're going to create our fraction f1 is equal to a new fraction, num denom. Then we'll ask for our other numerator, and we'll just reuse num and reuse denom. And then we'll build our fraction f2. And then we'll go ahead and say fraction f3 is equal to f1 dot add f2, and then we'll say f3 dot reduce, then f3 dot display. All right, so we're going to ask our user to give us a numerator and denominator, and we'll build a fraction. Then we'll ask them for another numerator and denominator. We'll build another fraction. Then we will add those two together, storing it in a fraction, ask that fraction to reduce itself, and then display it. So please enter a numerator. So we'll do 3. Please enter a denominator. We'll do an 11. Please enter another numerator. Let's do 1. Please enter a denominator. Let's do 17. And there's our answer, 62,187. Make sense? All right, so that is how we do user input, and that is our object example. So let's go ahead and get that up on GitHub before we go any farther.
All right, dumb question.
Go ahead.
I didn't know to ask twice.
I asked once right here, read it in.
Oh.
I asked once right here, right here.
Got it,
Yeah. So it's because we asked them to do it twice.
All right, got it. It makes sense now.
But as a hint, and we'll see this with our Tic Tac Toe, and I know I'm kind of rushing a little bit, but I want to make sure I give you a fully functional Tic Tac Toe here so you have something to work off of for your assignment. But for Tic Tac Toe, you're going to probably, well, in your homework, you're going to keep asking them in a loop until somebody has won. In this case, I just needed to haphazardly bring in 2 fractions, so I just asked them twice and just said we're good. All right, so I went ahead and I added everything to our Git repository. I'm actually going to start a new repository for our Tic Tac Toe. So this will be our last thing for this one. Notice it shows that we have a new file in here called fraction, but the latest commit for driver will have the fraction stuff in it to show you the IO stuff. So I'll go ahead and do a git commit-m fraction. Well, let's do fraction object and user input. And then we'll do git push. Oh, I'll just show you that it's up there. So here's our fraction object and user input. 2 guys here, so you have all your scanner stuff in here. And then we should have our separate second file. Let me just go back here. Here's our fraction file right here. Okay? So that is that one. So let's go ahead and let's start a new project for, we're going to do this one Tic Tac Toe. So we're going to say File, New Java Project, CSC535 underscore fall 2016. No, this is spring, right? Spring 2016 underscore Tic Tac Toe. All right. Perfect. Now, I'm going to go ahead and create my file that's going to run this whole thing, and I usually call that a driver. So here's our driver. And then I usually just do a system.println. Hello, make sure everything's zigging. And it is, so we have a working program there. Now, everybody's familiar with Tic Tac Toe in here? We know what that game is? Just a quick Tic Tac Toe, Tac Toe.
It's a game.
Right here, this guy. The X's and O's one. Okay, familiar with this one? Yeah. All right.
It's an exercise in utility.
No, I won Tic Tac Toe against my wife this weekend at Buka. Then she wouldn't play anymore because I cheated. I went twice in a row. Only way you can win. Well, my wife's pretty intelligent. I'm the dummy. What was I talking about? Oh, right, Tic Tac Toe. All right, so I'm going to create a object. So we're going to do everything in terms of objects. So as I'm going through this, think about this in terms of what we did last class, where we're breaking everything down to little tiny functions, little tiny methods. Now we're going to break our tic-tac-toe game into individual objects. So as we start thinking about things in the object-oriented world, imagine you and I sitting here playing tic-tac-toe. What's involved? Well, we have the board sitting in front of us, right? That's probably was drawn, ours was drawn in crayon. I took a kid's menu. It's a whole nother story. Right? So we have the board sitting here in the middle, and the board is showing us, it's displaying it, and then we have a couple of players that are playing the game, right? So we want to think about those objects almost like it's a movie scene or a scene in a play. Who's there, who's involved, and how are they interacting with each other? So I'm going to go ahead and create a board. That's going to be our game board. In fact, let's call it game board. All right, so here's our game board. Now, in order for tic-tac-toe to work, we're actually going to, well, in order for it to benefit us the most in terms of our homework assignment, we need to implement our game board in terms of a two-dimensional array. Okay, so at this point we've looked at one-dimensional arrays, so that is an array of integers. What a two-dimensional array is an array of arrays. That's how it's actually implemented under the hood. But from our perspective, it's a grid. Okay, so when we look at tic-tac-toe here, this is 3 columns, 3 rows. It's a 3 by 3 grid. Right? Connect 4, I think, is like a 7 by 6 grid. Okay, so I gave you a link to go and learn about tic-tac or Connect 4 for your homework. All right, so we're going to go ahead and create a grid. And you're going to see the syntax is what we've already been used to. So I'm going to have a private, let's call this guy a, we'll do it a character array, char array, and this guy is going to be called the board, and then we're going to have our constructor for game board here, okay, and our constructor is going to fill in the empty board. Okay, it's going to give us our empty board, and what we'll do is we'll just put little underscores wherever there's an open spot right now, because our whole board is going to be displayed in just text-based. We're not going to have a whole lot of graphics going on here. So the next class, the 537 class, we do Android. So we'll actually create graphical stuff. So I use Android programming in there. So in any case, we're going to go ahead and we're going to create our board. So we'll say this dot, the board, is equal to a new char array, 3 rows, 3 columns. Okay? Now we're going to go through and we're going to fill up that array. So this is our normal. Remember I mentioned a few minutes ago this is an array of arrays. So we're going to use our normal loop, int I is equal to 0. Actually, I'm going to do this inside of another function, if you'll let me. So we're going to call this one private void clear board. And this guy's going to have a loop for int I is equal to 0, I is less than this dot, the board dot length, I plus plus. And then inside here we'll have another loop for int j is equal to 0. J is less than this dot, the board at bucket I dot length, j plus plus. So for each row, go through each column. Make sense? So notice I'm saying the board at bucket I, that guy is an array that has a length. It's an array of arrays. But for us, we can think of it as a grid. So that is to say that this is row 0, column 0. This is row 1 or row 0, column 1, row 0, column 2, row 1, column 0, row 1, column 1, so on and so forth. Okay? And we're going to go ahead and just fill up our board with a bunch of underscores. So we're going to say this dot, the board at bucket I, j is equal to the character underscore. Make sense? All right. Now I'm going to steal most of that code. And we're going to say private void display, or print, whatever. And this guy's going to know how to display a board. So we're going to say system.out.print this dot, the board at bucket I, j, and then we'll throw a space after this. Actually, we'll see how that looks. We'll tab it. That's only going to be one character. Yeah, let's tab it. It'll look better. All right, and then outside of that loop, we'll do system.out.println. That'll kick it down a line. So print just shows it on one line. So this is going to print out column 0, column 1, column 2, kick it down a line, move to row 1, column 0, column 1, column 2, kick it down a line, so on and so forth. So now a board knows how to display itself. When we first create a board, we'll instantiate the two-dimensional array, and then we'll go ahead and tell the board to clear itself. But we also have allowed the board to clear itself in general as a private function here in case we need to clear the board for like a second game or something like that in the future. All right, so this is going to be our initial game board. So we should be able to create a board and tell the board to display itself. So we'll go ahead and say game board is equal to new game board. And notice our constructor here took in no parameters. So we still need to call the constructor, but we don't have to provide it anything for it to work. It just works, at least right now. And then we'll go ahead and say board dot, oh, did I make that private? I did. This should be public. So that method should be a public method so we can actually display the board from other places. And we'll go ahead and run this, and there's our board. Okay, so now let's go ahead and write a function to make a move. So we're going to make, a move is going to be made with the letter X or O, so a char, and then its row column. Make sense? So we'll write public void make move. Actually, let's have this guy return a Boolean, whether or not the move was successfully made, because we can't put an X on a place that already had an O. Make sense? So public Boolean make move, and this guy will take in a char, move char, and int row, and an int col. And we'll ask the question if this dot the board at bucket row col is currently equal to an underscore, then we're allowed to make the move, right? So we'll say this dot the board at row col is equal to move char, then we'll return true. Otherwise, we'll return false. So this allows us to try to make the move on int row, int col. If we're allowed, we'll make the move and return true. Otherwise, we won't make the move and we'll just return false. Okay, remember, return makes the method immediately end. So now I should be able to make a few moves. Let's see. Well, let's just make some moves on it. Board dot make move x. We'll put it in the middle. So 1 1. So we'll tell the board to display itself again. So this should have an X there in the middle. The board displayed twice. Probably. That'll be our separator for our board. All right, so here's our board with the X in it. All right, make sense? So we now need to alternate between players. So we actually have a game that's going on here. So him and I sat down to play the game Tic Tac Toe. Who's involved in this game? 2 players, a board, and it's governed by the game rules of Tic Tac Toe. Make sense? So we need some more objects here. So we need some players. And from our perspective, a player has a name and a player has a move character. So I'll be X's, he'll be O's. Make sense? So player 1, player 2. So let's go ahead and we're going to add another class here. New class. We're going to call this guy a player. A player will have a private string name and a private char, move char. And then we'll have a public player. This guy will take in a string name and a char, move char. And we'll set this dot name equal to name, this dot move char equal to move char. And then we probably want to go ahead and give ourselves getter methods for name and move char. So I'll right click, we'll go to source, generate getters and setters. I'll click on both of these and we just want to get the 2 getters out of that. So now a player can give us his move char and can also give us his name. All right, we might need that. All right, so we're going to say that's all a player is right now, is that simple stuff. Then we're going to go ahead, we're going to create another class. In fact, actually, just to test this real quick, let's come out to driver, and well, let's keep trucking here for time. So I'm going to do new class. So we're going to call this the game. Okay. So the game itself is going to house a game board, 2 players, and it's going to govern the rules of the game. Okay. So here's our game. This guy's going to have a private board. I'm sorry. Private game board called board. He's going to have a private player 1. I'm in a different language here. Private player named player 1. A private player named player 2. Okay, let's leave it at that for right now. Then we'll go ahead and create our constructor, public game. We're going to say this dot board is equal to new game board. That'll generate our board for us. This dot player 1 is equal to a new player 1, and he's going to be X's. This dot player 2 is equal to a new player 2, and this will be O's. Okay. Now, these are the people. So we've just sat down to the table. We're ready for our Tic Tac Toe death match. All right. So the game is in session. We have a board that's been put out in front of us. The two players have arrived, and now we actually need to play the game. Okay. So let's create a public method called play. I'll just call play. All right, so the very first thing we do when we play the game is we display the board. So we'll say this dot board dot display. Great. All right, so we're going to display the board. Now we need to have player 1 go. Correct? So what happens next? Player 1 goes. We make his move. Player 1 gets to keep going until he makes a legal move. The good thing is our board tells us whether the move we just made is a legal move or not. Okay? And then we check to see if there was a winner. Right now we're not checking for winners. So let's just let moves go for right now. And we'll just let them keep going until they just fill the board. Okay? So we're going to go ahead and display the board. Do we have to do that at least once? Yeah, probably got to display the board at least once, right? So this might be a good time for a do while loop. Right? So do this while, for right now I'm just going to put a true in there. We probably want to say something like while there is not a winner, something like that. Okay, so we'll tell the board to display itself, and now we want to let player 1 go. So we need to get the move from player 1. So we need to figure out how to get a move from a player. That means a player needs to provide for us a row and column. That make sense? All right, so we're going to go ahead and we're going to teach a player. Let's see, do we want to do that here? Probably do it here. So we're going to write a function here. Private void get move from a particular player, named player. And this guy is going to prompt the player for a row, prompt the player for a column. Okay, so system.out.println, or print, please enter a row. And then I'll go ahead and prompt for the column, and then we'll write the other thing in the middle. Please enter a column. Now, in order to read stuff in, we need to have a scanner. So we're actually going to go ahead and make that scanner up here. So private scanner input. This guy, well, is equal, well, let's just do it. We'll do it in the constructor. So we'll say input is equal to a new scanner system.in. Then we need to import java.util. All right, so the game is going to require a scanner, even though that's not something that we typically would think of as an attribute. So that's kind of an extra guy we have there. Even though when him and I are sitting here in our game world, we are asking each other for input what our next move is, right? This is just kind of one of those silent partners, if you will. So we're going to need our scanner. So down here, when we get the first move, we'll go ahead and say int row is equal to this dot input dot next int. And then we want to get the column. This dot input dot next int. All right, so this is going to get the move from the player, and we want to do this. So we're going to try to make our move now, right? So we're going to go ahead and say this dot board dot make move with what move character? Player dot get move char. Row is row, column is column. Now that guy's going to return a true or false, right? So I'm going to say do all of this stuff over and over and over and over again until as long as this guy right here is equal to false. So we can say not that, or we can say, well, that is equal to false. So as long as the move we just tried to make is not a legal move, ask him for a row and column again and try the move again. All right, and I'm going to go ahead and whenever we have an indenting problem like this, because I added something, you can highlight it, right-click, go to Source, and go to Correct Indentation, and that'll fix the indentation for you. All right, so we're going to get a move from a player. We'll pass the player. We're going to ask him for the row, ask him for the column, try to make the move. If it doesn't work, we'll ask him again. If it does work, we're done. Move has been made. Make sense? Okay. So what are we going to do here? We're going to display the board, and then we're going to ask a player to make a move. Now we want to toggle back and forth between the current player's move. So we're going to say player, cur player. We'll start this off as player 1. I like to say this dot player 1, but it's not required. So we'll go ahead and say this dot get move from cur player, and then we'll go ahead and toggle cur player. So if cur player is equal to this dot player 1, then cur player is going to equal this dot player 2. Else cur player will equal this dot player 1. So that should flip back and forth between player 1 and player 2. So each time through, we'll show them the board, we'll get the move from the current player, we'll toggle to the other player, and then we're going to check the board for the winner. Make sense? So right now we're saying while true. We need to check the state of the board to see if there's a winner. So this is the last part of our game here. Okay, there's only 8 ways to win. All right, so let's go to our board and let's teach our board how to check for winner. Public Boolean, let's call it has winner. All right, and this guy is going to check for the 8 ways to win in this particular case. That is, all of the characters across the top row, middle row, or bottom row are the same. All of them up or down are the same, or the diagonals are the same. Make sense? All right, so we're going to say, we're just going to create some Booleans. Let's see here. Actually, I'm going to be pretty verbose with this because if we check to make sure they're the same, we'll get a false positive because we'll have matching underscores. All right, so I'm going to specifically say, are they all X's or are they all O's? So we're going to go ahead and say Boolean row 1 winner A is equal to this dot the board at bucket 0 0 is equal to an X, and 0 1 is equal to an X, and 0 2 is equal to an X. And here I can stack these guys like this. So that is row 1 winner A. Here's row 1 winner B. O, O, O. Row 2, row 2. Row 3, row 3. Probably go like 4 minutes over, but I want to give you a full working thing if that's cool. If you have to book, you can. I'll have it recorded. So that's the row winners. So now we do the column winners. So this is call, 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 call. All right, and this will be 0, 0. This will be 1, 0. This will be 2, 0. 1, 0. 2, 0. All right, and this is going to be 0, 1, 1, 1, 1, 2. So that is, yep, that's for column 2. So this is row 0, column 1, row 1, column 1, row 2, column 1. That. This will be row 0, column 1, row 1, column 1, row 2, column 1. Row 0, column 2, row 1, column 2, row 2, column 2, row 0, column 2, row 1, column 2, row 2, column 2. So that's column winners. Okay. And then we need diagonal. Is it diagonal? How do you spell diagonal? It's not right. Oh? Is that right? That's a weird looking word. Alright, so diagonal winners. Diag 1, winner A. Let's actually, we'll steal these. I don't want to do it as big a bulk. Dia 1, winner A. Dia 1, winner B. So this will do left to right. So this is 0, 0 is X. 1, 1 is X. 2, 2 is X. Or 0, 0 is O. 1, 1 is O. 2, 2 is O. We'll steal this, and we'll have our diag 2 winners. So this is going to be 0, 2 is X. 1, 1 is X. 2, 0 is X. Or 0, 2 is O. 1, 1 is O. 2, 0 is O. All right, so those are all our possible winners. So we want to return row 1 winner A, row 1 winner A, or row 2, row 1 winner B, or row 2 winner A, row 2 winner B, or row 3 winner A, row 3 winner B, or col 1 winner A, col 1 winner B, or col 2 winner A, col 2 winner B, or col 3 winner A, col 3 winner B, or dia 1 winner A, dia 1 winner B, or dia 2 winner A, dia 2 winner B. If any of those are true, return true. Let me just highlight all this and fix the indentation real quick. Source, correct indentation. Okay, so now a board knows how to tell us whether or not there's a winner. So finally, in our game, we're going to keep playing. Display the board, get the move, swap the player. We're going to keep playing as long as this dot, we call it this dot board dot has winner is equal to false. As long as there is not a winner yet, keep playing again. So that means if we get past this, the winner is not the current player, it's the previous player. So if current player is equal to this dot player 1, then we're going to say system.out.println, the winner is this dot player 2 dot get name. Else player 1 get name. We'll spit out the answer. So finally in our driver, game G is equal to new game G dot play. Please enter a row. So we'll do row 1, column 1. So there's that. Then we'll do row 0, column 0. There's that. We're going to force a win here pretty quick. Row 0, column 1. There's that. Row 2, column 2. There's that. And finally, row 2, column 1. The winner is player 1. Make sense? So. All right, so let me go ahead and I'll create a new project on GitHub and then I'll post it up there. So I'm going to actually create this as a Tic Tac Toe game, so you'll be able to look at this as a starting point. So I'm going to steal, so create new repository CSC535 underscore Tic Tac Toe. All right, so we'll create that, and then I need to go into 35 underscore spring. CD into this guy, CD into source. Get init, get add star, get status. We add the remote there. Get commit -m initial commit, and then finally we'll push it. And now it should be up there. So there's Tic Tac Toe. So I'll go ahead and copy this and I'll add it to your assignment so you have it. So your homework is to write Connect 4. This is a working version of Tic Tac Toe. What you'll actually find is the check for winner of Connect 4 is less tedious than this. It'll involve loops and stuff, but Tic Tac Toe check for winner is like stupidly tedious. Right? We just created like a whole bunch of ors and stuff. All right. I will see everybody on Wednesday.